student. Today I will discuss some important theorems. Okay, so before I discuss about the polar form of a complex number, modulus, as well as argument of a complex number, all those things already we have discussed. So just you try to remember, if we write like this way, r of cos theta plus I of sin theta, then here this r is called the modulus, right? R is called here modulus, right? And this is we write like this way, we do not write this way, right? And this theta is called the argument. So argument of z is nothing theta. We do not like this way, right? And also you just remember this complex number we can write like this way also. So this thing already we have discussed, z equal to r e to the power I theta. So sometime we use this format or this format, right? And here this r and theta are the modulus as well as argument respectively. Okay, so now you see some properties of modulus are there. Already we have discussed, but you see this modulus is nothing, modulus of e square is nothing, this is this value z into z bar. What is z bar? Z bar is the conjugate of this complex number, right? So you see how we get this value. You see, if we consider the complex number like this way, this is x plus iy, then what will be the modulus of this one? This is x square plus y square of whole square, right? Already we have discussed this thing, so this way we can easily find the modulus. So from here, what will be modulus of z square? This is x square plus of y square, right? Now you see this modulus square is nothing, real part square into plus imaginary part square. So now you check here whether this values is equal to this one or not. You check here what is our z here, this is x plus iy, and what is our z bar, this is x minus iy, right? Because conjugate of this complex number is this one. I think already you are familiar with the conjugate of a complex number, right? This thing also we have discussed. How we can find the conjugate of a complex number? Just you need to change the sign in front of the imaginary part, right? You see here imaginary part is y, but here imaginary part is minus. So just you change the sign of the imaginary part. Yes, you will get a new complex number that is called the conjugate of the previous. A square minus b square formula, right? So here will be this one, right? A square minus of b square. Okay, here you see x square and I square means minus 1, and that minus that this minus will be plus, and y square. Here you see this is nothing equal to the modulus of z square. That means what we can say here, modulus of z square is nothing, z into the conjugate of that z, right? So this is an important formula you need to remember. So by using these properties we can easily verify or we can easily prove this theorem. Here you see what is the theorem here. The modulus of the product of two complex number is the product of their moduli. That means if we consider z1 and z2 are two complex number, then product of modulus of their product is nothing, the product of their moduli. This is we need to prove, right? This is we need to prove here. Z1 and z2 be two complex number, right? Complex numbers. Okay, we consider. So therefore z1 into z2 of modulus square, if we write like this way, then what will be this value, guys? This will be z1 z2 into z1 z2 of bar according to this theorem. Here you see the modulus square is z complex number and its conjugate. So here you see this is our complex number and its conjugate. So from here z1 z2, and we know that conjugate of z1 z2 is nothing, conjugate of z1 conjugate of z2, right? This is the property for conjugate. This thing already we have discussed. So and again you see, since the complex number satisfy the associative property with respect to multiplication, so just you can rewrite this thing, z1 z2 bar and z2 z2 bar. This way you can write, right? Now what is this? This is our modulus of z1 square, and what is this? This is modulus of z2 square. So finally from here z1 z2 modulus square, we get here modulus of this one z2 modulus square, this is right. But here you see modulus of z1 z2 or modulus of z1 z2 all are positive number, right? And since they are positive, so from here we can write this value, this square we can remove, right? Because we have a formula, suppose a square equal to b square, this will imply a equal to b when a and b both are positive number, right? So since modulus are always positive, so this square we can cancel. So this is the theorem which we need to prove. So this way we can easily prove this theorem, right? Hope you can easily prove.